What are the different types of encoding and decoding types in physical layer is what they ask in most of the exams and also in interview. The first form of encoding, I'll explain it very cleanly. Okay, NRZ, L, non-return to zero level, non-return to zero level. The idea here was 1, 2, 3, 4, 5. Okay, NRZL, we have zero voltage here, we have positive voltage here, let's suppose 5 volts, we have negative voltage here, let's suppose minus 5 volts. Okay, the idea here is non-return to zero. It means they are converting bits into signals, but the signal never returns to zero. I mean, if the signal doesn't land here in this graph, it will go to minus, it will go to plus. So the basic idea here is 1 is represented by positive voltage, 0 is represented by negative voltage. Done? So starting with 0, clock 1, clock 2, clock 3, clock 4, clock 5. Why am I adding clocks again and again? I told you physical layer is responsible for bit synchronization, nothing but getting the sender and receiver synchronized. Okay, synchronize it with some clock. 0, again 0, now comes 1, it will go here 1, it will come here 0, 0, it will come here 1. Fine, this is nothing but non-return zero level. Now what are drawbacks here? The major drawback, I told you the signal never returns to 0, and I told you now by this you can determine only if bit changes, only then the voltage is changing, right? Suppose the bits are 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Suppose, then the graph will be like swing, 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 swing. It will be like this: negative voltage, positive voltage. Okay, it will be like this. Now, as the graph is like this, the receiver will face a problem, will face a wandering problem, baseline wandering problem. Bro, if the graph is constantly like this, and let's assume there is some error in clock synchronization, when will I get to know when the one bit has ended and the next bit has begun? Am I right? To see, this is 1 clock, this is 2nd clock, this is 3rd clock, this is 4th clock. This is 0, 0, 0, 0. Okay, 0. When will receiver get to know this 0 has ended and the next 0 has started? If the receiver and center clocks are perfectly synchronized, it's okay. It's okay. But if they miss by a certain bit, gone, it will think these both are 1 zeros. These both combined is 1 0. And these both combined is 1 0. Data vanished. Okay? Then people who are genius, not too genius, but yes, genius when compared to these people, they came up non-return to 0 only. They came up second form of non-return to 0 called as non-return to 0 I. Second form of non-return to 0. Non-return to 0 inverted. I told you in NRZL, positive voltage represented 1, negative voltage represented 0. Okay, what I will do, 0, 1, 0, 0, 1, 0, example, what I will do is, if the bit value is 1, I will shift at any cost. I will shift from high to low or low to high. It says if it is 1, I will shift. If I am in high, I will go to low. If I am in low, I will go to high. But if it is in 0, I will never shift. Okay, nice mind games. High to low or low to high. It depends wherever it is. Now, we have graph here. We have 6 bits. 1, 2, 3, 4, 5, 6. Okay, first one is 0. As it is 0, the basic thing is it will start from negative voltage. Okay, it will start here. Now it is 1. I told you 1 is shift at any cost. Shift to positive voltage. Positive, negative. It will shift here. 1, 2, 3, 4, 5, 6. 5. Shift. Now it says it's 0. 0 means never shift. It will stay here. Again 0. It will stay here. Now 1. Shift at any cost. 3. Shift. 0. It will stay here. Nice. They are shifting. Nice. One more guy who was jealous of this guy. He came and told, this also has a major drawback. Okay, you are solving a problem of bits not remaining at the same state. Okay, but the major drawback is, what if there are most of the zeros and only few ones? These also will remain at the same state. As I told you, zeros never shift. Right? There will be a small shift and again no shift till there are zeros. Drawback? Right? So what I was trying to explain was, in both of the NRZ encoding schemes, there is a baseline wandering problem. Now, I will explain you about return to 0 encoding scheme. RZ. That was NRZ. This is RZ. So what this was saying, okay, in both of the above schemes, NRZL and NRZI, signal is not written into 0 or the signal is getting stuck at one place, right? So now, return to 0 scheme said, as you are facing baseline wandering problem, I am going to solve this issue by forcing each and every bit to return to 0 at any cost. Okay? Now, we will use the same scheme. 1 represents positive voltage, 0 represents negative voltage. But at the middle of the time period of the bit, the voltage level drops to 0. It will come to 0 at any cost. Okay? 1 is represented by positive voltage, 0 is represented by negative voltage. Okay? Now, we will draw a graph here. Suppose we have binary value 0, 1, 0, 0, 1. One time period, second time period, third time period, fourth time period, fifth time period. Okay, we have voltage level 0. Here we have positive voltage. Example 2.5 volts. Example 2.5 volts. This is minus 2.5 volts. This is used to represent 0. This is used to represent 1. Okay. Now, as it is a 0, I said 0 is represented by negative voltage. Okay. Here it will come down, the graph will come here. Now it will come till the half time period. Time period 1, time period 2. I mean, time period of bit 1, time period of bit 2, time period of bit 3, time period of bit 4, time period of bit 5. Okay. At the half of the time period of bit, any bit, all bits, this signal will return to 0 at any cost. So now the graph is like this. Now it will come back as 0 here. It will come back as 0 here. Okay. As it comes back as 0 here, now the next bit is 1. I told 1 is represented by positive voltage. The graph will go up. Okay. It will come like this. But at the middle of the bit period, it will draw back to 0. Okay. And now the next bit is 0. It will come here. 0 is represented by negative voltage. It will come here. It is like this. Come back here. Again 0. Again it will come here. Again it will come here. Again like this. Come back to 0. The last one is 1. It will come here. It will go here. It will go. This is the graph of return to 0. Understood about this? Understood about this? So, From this we can say, okay, the baseline wandering problem is solved, because if you see, even if there are two consecutive ones, the signal is not getting stuck at one place. It is going back, okay. But the second most important issue arises, synchronization between sender and receiver. Now what is synchronization? First of all, the receiver must exactly know when one bit starts and when one bit ends. Am I right? Now suppose, let's take a basic example. If me and I tell you to copy my style, okay? To copy my clock sync, like per second, if I'm doing like this, you must also do like this. Let's see it physically, okay? I will tell you, if my hand is moving like this, your hand must also move like this, okay? And first you'll be differing. First you'll be like, oh, I can't understand his time, man. He's doing sometimes fast, he's doing sometimes slow. It will take time for you to understand me, okay? I am doing like this. Slowly you start copying me, right? In the same way, if the sender is operating like this, the clock is like this, and if the receiver is operating like this, it will encode 1 as 0, it will encode 0 as 1. Am I right? Yeah, that is the reason this has the synchronization issue.